Hello and welcome to my Google Summer of Code 2020 demonstration video. Over the course of the summer, I worked on the media IP streaming project over at Beagleboard.org. My project objectives were first, support the CTEC phase drivers implemented by Hendrix for GSoC 2016 to the Linux kernel version 4.19 RT for Beaglebone AI. The second step was to port the AVB driver stack, which was implemented by Indu for GSoC 2017, also to Linux kernel version 4.19 RT for Beaglebone AI. Therefore, all code has been refactored and modularized, and also the FDEC protocol has been implemented. The whole documentation for the project can be found under niklasvan.github.io/gsoc-overview. Now we're coming to the presentation of the first part, the implementation of the CTEC phase drivers. The status of the CTEC phase drivers is that all driver code has been merged into the Beagleboard 4.19 RT branch. Also, all created device tree overlays had been merged on July 1st. However, those had to be refactored with another GSoC student who worked on overlays to handle all changes which were made to U-boot overlays. The limitations of the CTEC phase drivers are that the drivers are working just for 4.19 RT and have successfully been tested for Beaglebone Black and Beaglebone AI. During the project, the objective came up to also port the drivers to a version 4.5 RT. However, that failed because the SPI GPIO bitbang drivers did not load on this kernel version. Now we're coming to the demonstration of the CTEC phase drivers. For the demonstration, the following setup has been applied. We have one Beaglebone AI with a CTEC phase. The CTEC phase streams 2 channels of audio data into an ADC, and this ADC records the audio data into a PC. To show you the working of the CTEC phase driver, we first list our playback devices. Here we see that card 1 is our CTEC phase. After that, we list all record devices. Here we just have the CTEC phase. Then we look at all loaded modules with the SND-SoC DaVinci CTEC phase driver listed. In the ALSA mixer, we can control our sound card. We have to press F6 and choose the CTEC phase. Here we can adjust the volume for DAC 1, 2, 3 and 4 and also set playback sample rates. Now we playback the audio file via the phase card and you should hear the result. After successful implementation of the CTEC phase drivers, the virtual AVB driver stack has been ported to the kernel version 5.4 RT. The driver code pull request is still open as of August 25. The virtual ALSA AVB driver has been ported to 5.4 RT because I realized that the kernel version 4.19 RT is quite unstable on Beaglebone AI. The limitations of the implementations are that the playback is only available for one stream between a AVB talker device, which is a Beaglebone Black in our case, and a BBAI, which is the listener device. Each stream can contain up to 8 audio channels. The output of the received audio can be played back via HDMI or can be written to a WAV file. The playback, however, is not synchronized. And also the FDEC detection is not working properly with the proprietary MAG solution. To demonstrate the AVB driver, the following demo setup has been applied. We have a Beaglebone Black and a Beaglebone AI. The Beaglebone Black streams the audio data via a cross Ethernet cable to the Beaglebone AI. The Beaglebone AI then plays back the sound via HDMI and you should be able to hear the sound. Here we see the console windows of both of our devices. On the right side is the Beaglebone AI, which is the receiving device, and on the left side is the Beaglebone Black, which is the sending device. To start the whole AVB stack, we first have to start the GPTP daemon on both devices. After that, we can insert the hardware-dependent module and then the AVB driver. When we did that on both devices, we are able to start the AVB test application. On the Beagleboard AI, which is the receiving side, we have to give the command line argument Y to receive the audio data and play back the audio which is received via the HDMI card. We send the audio data at 48 kHz and we send 2 channels. We choose L6 to log at log level 6. On the sending device, we are starting with the command line argument X, which is the send command. We send the file test mult period, which is a multiple of the period size. Now we can see how the file is transmitted and received, and we hear also the result. Another functionality of the AVB test stack is now shown. We can also play back the file and stream it to another file on the other device. Therefore, we start the AVB test application with the P argument, and on the receiving side with the Beagleboard AI, we start the AVB test app with the R argument. We want to record again 2 channels at 48 kHz and save this into the rec.wave file. After starting the process, we can see again how the audio data is transmitted and received. On the Beagleboard AI, the received audio data is written to a file. To show you both files, here is an Audacity project. On the top, we see the send file. On the bottom, we see the receive file. We can see that both files are equal in length, and when zooming in, we see that they are exactly the same in phase. And this is valid through the whole file. The last point is to show you the communication between Beagleboard Black and an Apple Mac device. Therefore, the following demo setup has been created. We have an Apple Mac and a Beagleboard AI, which are connected by a cross Ethernet cable. The purpose of this last demonstration is to show you the FDEC communication between the implemented AVB protocol for BBB and BBAI and the proprietary Mac solution. Therefore, we have to connect our BBAI with a Mac which supports hardware timestamping. We can check if the sound card supports hardware timestamping in the network settings as shown here. After that, we go to the network device browser in audio MIDI settings, and there should normally be our AVB device listed. However, the FDEC communication is not working properly. Therefore, the AVB diagnose program is started. Here we can see that we find the Beagleboard node. However, the sub-protocols of AVB are not working properly, and thus the FDEC communication is not working. Thank you very much for your attention, and if you are interested in more information, please check out the documentation page.